This is Bradley Needham. I'm going to be talking about STL algorithms, in particular the non-modifying sequence algorithms. The most common one you're going to see is the for each algorithm, and for each basically just does what it says. For each of the elements in the range that it's passed, it will call whatever function or functor that you pass to it. So why would I want to use the for each algorithm? Well, I might want to just iterate over a collection. And we can do that naturally with a for. Let's first create ourselves a collection, a vector of integers. We'll call it collection1, and I'll initialize it to some values. And then if I wanted to print out each of those elements in the collection, I could write a for loop. And I'm going to use the auto keyword here from C++11 equals collection1.begin. Iterator is not equal to collection1.end. And then I print out each element followed by a space. So let's run that. And that does what I want. It prints out every element. Now if this here was more complicated than a single line, I mean this is pretty straightforward. A maintenance programmer can look at that for loop and go, okay, he's iterating over every item in the collection. Here's from his beginning to his end. And he's printing out each element followed by a space. If this got any more complicated, I might want to, instead of putting the code directly here in the block of the for, I might provide a function of some sort, like print. Print is passed the value that I want printed. So let's go ahead and create that function up here. Void print takes an integer as its parameter, does what we were doing before, prints out that element followed by a space. So I run this, still works exactly the same way. But the other part of this is the loop. I still have to figure out what the loop is and what the loop's going over. And you get these little extra things here, like the iterator temporary that's available and the test that's happening and the increment that's happening. And all this is just stuff we know is always going to happen with a for loop. And it might be cleaner and a little more concise to say something like for each, pass in the range from the beginning to the end I want you to print. So now we've moved this down to one line of code, and it's probably, it was a small line, it didn't necessarily need to be moved that, but I feel sometimes this is a little more concise in saying, hey, for each element in this range, do this operation, which is print. I'll run it again, and again it prints out exactly the same thing. Another thing about the for each loop here is I could print a different range. I could say I only want to print starting at the fifth element. So it'll print out the fifth element here that I'm looking there on, right? So it starts at 9 and it prints all the way to the end. And by the same token, I could basically take off a few elements and print to a different end. Let's get it back to the full range. So now in this case, I'm passing a function and not a functor. I could pass a functor to for each as well, and if we change this print function to a functor, we're going to call it create a struct print, make sure to override the operator paren. So this will still work exactly the same as before. The only difference here in the for each is I now need to create an instance of that print functor. So this is creating a unnamed temporary of the type print. So I run it, I get my printing of the full range. An advantage to the functor is that I could create a functor that had some sort of state, like let's say it held a string for the delimiter, and we can have a constructor that takes a string. Then instead of printing out a space, we would basically print out whatever the delimiter is that was passed in. So now you can see that this is a constructor call for creating an unnamed temporary, and I can pass, say, a colon in there instead of passing in a space, and I run it, and we can see down here that what is being printed is the value followed by a colon. Let's make that a space. Okay, let's look at some of the other non-modifying sequence algorithms. This is for each. There's also one called find. And what find does, find returns you an iterator to the first occurrence of what you're looking for. So example, let's say I want to look for the value 9 in my collection. So I can say find from the beginning, start at the beginning to the end, find the value 9. And what this will do is it'll pass me back an iterator to this value, which is the first value found. So let's go ahead and simply, instead of printing out all the elements, let's print out just the elements starting at that location. Prints starting here, so 1, 2, 4, 8 were all missing from this output because we started at the iterator that was returned from find. Now, of course, you want to check to make sure that you actually get a valid value back from find, because what if I went searching for the value 11? That wouldn't be in the collection. So I want to make sure if iterator is not equal to the ending point, wherever the ending point of my find was, it's not equal to collection1.end. Then I'm going to go ahead and do my for each here. Otherwise, I'm going to print out not found for that, and we get not found because we were searching for 11. If I want to search for 6 and run it, I can find the 6 starting here at the end. Now notice there are multiple values in here, so I could find the first or the second one. Now find is always going to find the first one, so if I wanted to find the second one, I can check the range and look after I find the first one. So in this case, I might say, okay, well, find the first 9, let's say, and then use that iterator to find, let's say iterator again, to find the second one. So after, then find 9 again, right? And I might find something else in there in this section, right? And now, see, it finds the second 9 and prints out that to the end of the collection. Okay, so there's also a find algorithm that uses a predicate rather than just equal. So instead of looking for, say, in particular, the value that equals 9, finding in the collection the value equals 9, I might want to find the first odd value. When you're dealing with STL collections, the way you can tell, a lot of them follow this pattern, that if they're using a predicate, they have the suffix if on them. So this is find if. So instead of find the value 9, we want to find the value if it happens to satisfy this particular predicate. So let's go ahead and use our isOdd, and we'll pass our unnamed temporary of our functor object isOdd. And then what that should do is basically this should get to us what? It should get us 1 right off. Okay? So let's go ahead, let's change this to an even number as well. Change this to 6. And that way it should go all the way out here to 9 before it stops. And there we go. It's finding that odd value here. It's saying this is an odd value, and that's the first odd value that it encountered in our collection. If I move my collection, so let's say if I change this value to 5, so that'll be the first odd value, and run it again, then of course I get that first odd value found through the rest of the collection, which is what I'm printing out. It's another algorithm, which is count. And count can basically do this very similar to the way find works. If I say count, and I'm not going to use isOdd, I want to count all the 6s, all right? Or I want to count all the 5s, let's say. I'm going to count all the 5s. Here, auto basically gives me the type of the variable that this would be. So this function is no longer returning an iterator. It's actually returning a size t, which is actually returning the size type of the iterator type, but it's pretty much always a size t. I just want to print out the count. So cout count or number of 5s equals the count that was passed, and I hit return. And the numbers of 5s is 2, and I can see that 1, 2, there's no other 5s in there. If I change that to say I want to look for the number of 3s, then the number of 3s is 1, and so on. Count also has a version that takes a predicate, so I can count according to a predicate. And again, the predicate I might want to use is, say, isOdd. So I pass in the isOdd predicate, and the number of odd numbers in my collection, and the number of odds is 6, and let's see if that's right. So we have 1 odd, 2, 3, 4, 5, and 6. So there we have it. We have 6 odd values in my collection, and I can find that using COUNTIF. Alright, so there's several other non-modifying sequence algorithms in there, things like find end, find first of, adjacent find, mismatch, besides the ones we've gone over, and some newer ones in C++11 like any of and none of. But the other ones I want to go over here, because of their signature and the way they operate, are equal and search. So equal is interesting because equal takes 2 ranges. So there's 2 ranges, so I'm going to use 2 collections here. So I'm going to look at the 2 different ranges. And the way it takes the ranges is the first range is specified from the beginning to the end. So I'm going to print out, so it's going to return to me a bool. It's going to take a first range, and we're going to use collection 1 for that. Collection 1 begin and collection 1 dot end. But the second range that it only takes the beginning of the range. So collection 2 dot begin. So if I run that, that should return me true, right? Because the collections are all the same. However, it's important to note when you see a algorithm in the STL that starts with one range and then just the beginning of a second range. And the thing is that this algorithm will go over all of the elements in the first range, and it will expect that there are enough elements in the second range that it can also go over that many elements in the second range. So example, we should not pass something like this, where column 2 is smaller than, or collection 2 is smaller than collection 1. And the reason why is, yes, it will find that it doesn't equal when it basically does a compare here between the number 4 and the end iterator. But remember that this value here is unknown, and so you enter into unknown behavior, right? Undefined behavior. Basically, because what if the memory that's pointed to there does happen to be a 4, it may continue to think that it's equal and then not report back that it's not equal until it hits the 7. And also, you shouldn't be dereferencing memory that you don't actually own. So again, we don't want to have this range be shorter, and especially when we start talking about the modifying algorithms, because the modifying algorithms really assume that you're going to have full values, enough values in collection 2 that satisfy iterating over everything in collection 1. Now, of course, you could do it this way. This is fine to have more values in the second range, and then you notice that this still comes back as true because it's only going over the elements that are part of collection 1, and all the values in collection 1 from the beginning of collection 1 to the end of collection 1 do equal the values in collection 2 up to that point where it actually ends the range. Okay, so the important thing about equal is you have this, you'll find this in other STL algorithms, that if you have a starting range where you give a begin and an end, and then your second collection here, the second range, you just give the beginning, you got to make sure that it has at least this number elements from collection 1 in it and valid. Alright, so the last one I want to go over real quickly is search. And search does just what it sounds like. It searches for a sub range within the range, the first parameter range. So it's going to return an iterator as well. So I'm going to use auto iterator and search. I'm passing the first range, which in this case I'm going to switch these values and make collection 1 be the complete version again. And search is going to look for that range. So in collection 1, it will search for a subrange that matches the pattern in collection 2. And we will go ahead and print out for each element starting at iterator to collection 1 dot end. We want to print those values out. All right, so let's go ahead. So what we should expect to see is this end part of the collection 1 range, because once it matches the 547, it'll show that and give us the beginning iterator at that. So there it is. The return value is the iterator in collection 1 where that subrange actually starts. I hope this helps.